right, so here's kind of a cool example of circular motion. This is an event that is shown in the Olympics, and it's really just a track and field event called the hammer throw. And it involves a metal ball attached to a steel wire, and it's spun around, as you can see this person doing, and then it's released. And because of what we learned about centripetal motion, when it's released, its velocity points tangent to the circular path. And so it'll move in a straight line once this person lets go. What we're asked to find here is the acceleration of the ball and the tension in the wire. The acceleration is going to be found using our centripetal acceleration formula. Acceleration is v squared over r. Okay, so in this case, our v is given to us as 29 meters per second. I'll leave the units in here for right now so we can see how they cancel out. And then the radius is going to actually just be the length of this wire. So that would be the distance between the person's hands, which would be at the center of the circle, and the ball. So that would end up being our radius. And so we would go through and do our calculation here, looking for 29 squared, and then dividing it by 1.21. And I get 695. Now, how do the units work out here? Well, the units, I had meters squared, meters per second squared. So that was meters squared over seconds squared on the top, and then the whole thing is being divided by meters. And so what happens is that one of the meters on the top cancels with this meters, and we do get our regular units that we expect, meters per second squared, for the acceleration. So it doesn't mean the same thing as it did before. It doesn't tell us speeding up or slowing down, but it is still a value of acceleration, and it measures how the velocity is changing, how the direction is changing. Then if we want to find the tension in the wire is the centripetal force. It's the thing that's pulling inward on the ball. So really what we're trying to find here is the net force. And so we would use the mass of the ball, 7.26 kilograms, times this acceleration that we just found, and we would multiply. Now, these units, they're a little bit harder to see how they work out, so we just kind of have to remember that the a kilogram times a meter per second squared does give us just our standard units for force, so 5,046 we'll call it, and that'll be in newtons. All right, let's take a look at another question. All right, so in this case, we have a woman on her bike rounding a curve, and we're given the radius of curvature of her path. So this brings up a good point. Not all problems involve an object actually moving in a circle. They might just be moving along a portion of a circle, and these ideas can still be applied. So we know what her mass is. We would really want to work with the total mass here because she and her bike are going along that circular path. Okay, so 60 kilograms is the mass we're going to be working with. And we are actually given the force in this case. So this is going to be our net force. That's the force, the centripetal force, that's pushing her to the right, it would be. That's pushing her along the circular path. What we're going to do is to first figure out what the acceleration is from that value, and then use that to figure out her speed. Okay, so we're kind of doing the problem in reverse from what we did on the previous slide here. So let's start with Newton's second law, sigma F equals ma, and I'll rearrange it so that my acceleration is by itself. So we are taking that 600 newtons and we are dividing it by 60 kilograms. All right, so hopefully you can do that one in your head, right? That's 10. A newton divided by a kilogram, it doesn't look like it, but that's actually meters per second squared. Recall that if you put standard units into a physics formula, you get standard units out. And so 10 would be our acceleration. Then we would want to use our new centripetal acceleration formula. Okay, in this case we're trying to find v. So let's again do a little algebra here. Let me multiply both sides by r, and then we would square root and flip the sides. So really what we're doing here is taking the square root of our acceleration times our radius. So the square root of 10 times 6, or the square root of 60. Okay, so that's the way we would work that out. Again, the units do work out because this is meters per second squared, and this is meters. So we would end up with meters per second, meters squared per second squared, and then that square rooted would give us our meters per second. And that comes out to be about 7.7 meters per second. Okay, so the first problem, we did things in more of a traditional order and got to the force, and then in this question we went backwards. Let's look at one more example. So this just brings up kind of a neat application of these circular motion ideas. If something has a very high acceleration, we often talk about its acceleration as a multiple of g. So recall that little g, the acceleration due to gravity, is 9.8 or about 10 meters per second squared. And so if something has an acceleration of 20 meters per second squared, we could say that that is 2 g's, 2 times the acceleration due to gravity. And so in this case, we're talking about a jet that has a maximum acceleration of 4 g's. And so that maximum acceleration of 4 g's we would think of as 40 meters per second squared. You're just multiplying it by the value of g. And then in this case, we are looking for the radius. This does not involve forces. This is really just an application of our new centripetal acceleration formula. And so to find r, we might do the algebra trick where we flip across the diagonal. And then that would tell us, let me do it down here, that would tell us our speed of 300 squared divided by the acceleration, which was 40, and that's going to find us our radius. Now that number is pretty big, 2,250 meters. Some people might state it in kilometers. That would be by dividing by 1,000. Okay, so sometimes you might see the answer written this way. You don't have to, but sometimes, sometimes we do see it, so we would want to make sure we understand it. Okay, let's add another question to this. What if we wanted to know how much time it took for one rotation? Remember that the period is capital T. That is the time for one cycle, one circle. So let's imagine that we wanted to find that value. If we did, we would then turn to the v equals 2 pi r over t equation. Okay, this is the one that relates how much time it takes to make a rotation to how fast the object is going. So again, I would use my algebra trick and I would flip across the diagonal. So t is equal to 2 pi r over v. So 2 times pi times this radius that we just found. We'll use the meters version. And then divide that by the speed of 300. Okay, and we'll go back and check in a second to see how the units work out, so that you make sure you sort of believe that this does work out. Plus, some people like to follow through with the units to make sure that they've done their algebra correctly. This comes out to be about 47, and that would be in seconds. So again, how do we know it's in seconds? How does that work out? Well, the 2250, that is measured in meters, and the 300 is meters per second. And so meters divided by meters per second, that's like taking meters times seconds over meters. When you divide by a fraction, you can multiply by the reciprocal. And so that's how we see how the seconds really do come through here.